I guess I'll begin with a word of prayer once I get up here. Dear Heavenly Father, we thank you for this day. Again, I thank you for this class and just ask you to help us use this time wisely just to cover a few more examples, Lord. In my prayer, Lord Jesus. Amen. So do you guys have any questions about anything in particular? Feel free to ask away.
I just need help with like just the circuits you're doing, not today, but the circuits from the rest of this week. I haven't understood those. Those have been rough.
Let's see here. Let's see here. I could try to make up an example. I don't know if we've had one quite like the one I'm about to do. All right, let's see here. Suppose we've got we'll say 20 volts here. I'm going to call that V1 so we don't have to write 20 volts every time. Then we've got R1 here, R2 here. To mix it up a bit, I'll throw in another voltage source here. I'll call that V2. We'll make it 10 volts. We'll put another resistor over here. Call that R3. And we'll put another battery over here. Call that V3, and we'll let it be, I don't know, let's say 40 volts just for the sake of whatever. And we can, we'll let, for the sake of just making things easy to think about, R1 is 1 kilo ohm, R2 is 2 kilo ohms, and R3 is 3 kilo ohms. All right. So with that set up, then we can, let me do some things a little bit different than I have before, just to try to, maybe the contrast of this and what I've done before might be helpful, possibly. So I'm going to make I2 go this way. I'm going to let I1 go that way. I'm going to let I3 go this way. All right.
Which way it goes.
You can define.
The current went one. The current had to go one way.
Mm-hmm.
That's what I assumed.
So if you're right, then I'll get a minus.
Okay. So okay.
Mm-hmm. But the thing is, however you define it, you get like voltage drops with respect to that current, plus minus,
but
plus
the
minus.
reason you can't tell which way the current is going is because of the extra batteries.
Right.
Okay.
Yeah.
Okay. Cool.
Essentially that. I don't know a priori. I don't know before the fact, like, you know, what happens. But, okay, so there's two things you want to do with these kind of problems. The one is, I mean, I guess we had to come up with another, so like obvious questions, what's I1, what's I2, what's I3? Another kind of like nagging question here, if we call this point A, you know, what's the voltage at A? If we define another place to be ground, and I'm gonna keep with my typical pattern, which has been to put the ground here, but that's not written in stone. You could put it somewhere else.
Does the ground like not matter as long as it's just there?
It defines zero voltage.
So at that point right there, zero?
I'm saying that this defines zero absolute voltage.
Okay.
Which is really just saying that I'm going to measure, voltage is always a relative measurement.
Yeah.
So you're always measuring between 2 points. So if I say that that's 0 volts, I'm saying that if I get, you know, 13 volts up here, it's relative to that point. Now, sometimes they'll ask questions about like two places in the circuit, like a A and a B, and you'll be asked for like the voltage difference, like VA minus VB or VAB. We can also ask about that. You have a question?
So like on a test, would we define where the ground is, or like how the current's flow?
I would define where ground is, and I would define the currents if I know it's good for me.
But
Because otherwise, there's infinitely many different ways to label currents on a given. Otherwise, I have to, every test I grade, I would have to grade in the light of the analysis of that student. I mean, there's still ambiguity once I make these choices in terms of like, you can write the equations down like in a clockwise sense or a counterclockwise sense, but that's not a big deal. Like that's a question of like plus or minus the equation. Okay, so the simplest thing though is to write down the law of conservation of charge, which is to say that charge is neither created nor destroyed, right? So what that means is that if you look at the point A, we can't have charge magically being created there, which means that the sum of the currents in has to be what?
it must be equal to the current at A.
The currents in have to equal the currents out. What's the currents out? Trick question. 0. I mean, another way to look at this, maybe this would be more helpful. Maybe you'd understand this more if I wrote it like this. I1 plus I2 is minus I3, right? You could see that, perhaps. I1 plus I2 has to be going that way, but that's minus I3. But you can also, just generically speaking, say the sum of all the currents in is equal to the sum of all the currents out. It's just if there's no currents out, then it just becomes 0.
So, but if we like chose I3 to be pointing the opposite way,
Mhm.
it would be
I1 plus I2 equals I3, yeah. It doesn't much matter as long as we write down, I mean, we can agree or disagree about whether my initial equation equal to 0 is greatest or if the thing I wrote after it is greatest, but we should all agree on the equation. Okay, yeah. So there's that one. Great. What's next? Well, and by the way, everything I'm doing right now is assuming that I can't use the easier ideas of just breaking it down to an equivalent resistance and just working it out bit by bit. Like that's always easier if I can get away with it, but I got multiple voltage sources here. It doesn't look like I can do that. Okay, so then you pick a loop. So I'll pick this loop here, and I'll draw a picture of what I'm doing. I'm starting here, and I'm going to go and start there and add the voltage drops or voltage changes around the circuit, so to speak. And so the way it works is you pick a convention, all right? You're going to either add minus to plus is positive, which is what I'm going to do. So I'm going to say I've got V1, and then you notice minus to plus, plus to minus. So then minus I1 R1. Notice over here though, now I'm not doing plus to minus, I'm doing minus to plus. So I do plus I2 R2. This has not happened in class for various reasons. But I need to make that happen in class because other people need to get confused by this. I mean, they need to face their confusion about this issue. And then, again, plus minus, right? So it's minus V2, and then I'm back where I started. So that's equal to 0.
So you define where the pluses and minuses are as well.
Right, but there's a system to it. The system is that the little thing, the little bar, and the big bar. So you're going from a lower voltage to a higher voltage. Little voltage, little bar, big voltage, high bar. So it's a voltage gain. And also, when the current's going in the same direction, it's a voltage drop. So like we go plus to minus, it's a voltage drop if the current's going that way. But the current's going the opposite way, so this is a voltage gain. So I just make my convention is to draw the direction of the current and to put plus minus to indicate voltage drop. Plus minus voltage drop this way, but we're not going this way. We're going that way around the loop. So it's a gain. Now, so if you just dogmatically stick to my silly conventions, you will not get confused. Now, if you try to go on the basis of your engineering intuition and half understanding mesh equations in other classes or something, then I can't help you. But I mean, there are. Okay. Anyway, so let's go like this here. All right. Wait. Yeah. So, right, if I go, starting here, which is kind of dumb, the first thing I get to is V2, right? And it's a voltage gain, so V2. And then notice plus to minus. So this time I do minus I2R2. See it? Because the relation of the current 2 is different. This loop, see, we're going like that. Whereas the previous loop, we were going like this. See, so the relation of the current with respect to the different loops is that's why I have a plus here, but a minus there. All right. Anyway, continuing. We do plus. It looks like plus I3R3. Yeah. And then, oh yeah, and I forgot to drop my plus minus over here, right? And then you said minus V3? Yeah, I think that's right. And then we're back where we started, so we have 0. There is another equation we can write down. The other equation we can write is the big loop. The big loop and I used to have a brown. I don't have it anymore. I'll use green. So if we start here and go like that, that's another loop. The thing is, the sum of the voltages, the sum of the voltage drops, or the sum of the voltage gains, whichever you want to look at it, the sum of the changes of the voltage as you go around the loop has to be 0 because you're getting back where you started. So you have to be back to the sum of the changes has to work out to 0. This is Kirchhoff's voltage law. All right, so let's go. So we got V1 minus I1R1. Some of this is going to be kind of like what we already did. But then over to here, we get plus I3R3 minus V3 equal to 0, I guess. Now, you don't need the big loop. Do you understand why? Like, what are the unknowns? I1, I2, I3? That's
but they're also equal to 0.
Right, 3. So yeah, 3 equations, 3 unknowns, right? So if you're counting 1 equation, 2 equations, 3 equations. Now these loops are always going to be distinct, but actually the big loop equation is probably it's somehow related to these other 2 equations and perhaps that one. I don't know. Like I don't want to say it's not useful. I just want to say it could be useful. Like it depends on how you get hung up on the algebra. How should we do the algebra then?
You could just use the one of the currents for the other 2 currents, and then put that into one of those equations.
Yeah, I guess I'm asking like a slightly more pragmatical question, which is, what's a good technique for doing the algebra here? Like, notice we've got kilo ohms for the resistances, we've got voltages for the volts. Like, it's a nice thing to like not write out the units and just work with numbers. So here's what I would do. I would like, this is fine, right? But I'd like to trade this first equation for something like, you know, let's say I1 minus 2I2 equals to, you know, well, I guess V1 minus V2. You know, divided by, well, let me get to the point here. What is V1 minus V2? I mean, technically V1 minus V2 divided by a kilo ohm to be fussy, but V1 and 20 minus 10 is 10 volts, right? So this would technically be 10 milliamps. But I say we might as well just write it as, you know, that's good. I was worried you're a student I'd forgotten. It's good, it's good.
Where did you get that equation?
This one. So I added the I and I1 and subtracted the I2 to the other side, and I kept V1 minus V2, and I flipped it. It's I know, I'm sorry. It is this equation. I know I'm slippery, but it's this equation.
There's 2 I2?
Well, R2 is 2.
Oh, you just plugged it in. Okay.
So what I'm saying is I don't even like what I wrote. I want to do I1 minus 2I2 equals to 10. I like that. With the understanding that I'm working in milliamps. My answers must be interpreted as milliamps if I do this. Yeah? Implicit units of milliamps. This one, I have, what's V2 minus V3? I get like, you know, how do you want to, I guess we could keep it like this. So we're going to have minus 2I2 plus 3I3 equals to V3 minus V2. V3 minus V2 is 30, right? If I didn't mess that up, that I'll do, let me underline. My hope is I have just taken this equation and rewritten it, okay? If you guys don't agree with me, do let me know. That should be enough. If we just look at, like, focus our attention on these 3 equations. Are you good? Good, okay. I think as I look at these 3 equations, we probably can solve them. Oh, it's really easy to solve. We can make everything in terms of I2 pretty easily. We can make everything in terms of I2. So like, notice that I1 is equal to 10 plus 2I2, right? And I3 is equal to like 30 plus 2I2 divided by 3, right? This is like, let me call this equation 1, equation 2, equation 3. So this is from 2, and this is from 3. Did you guys see it? And so then what I would do is I would plug those into equation 1, and that would give me, you know, I1 plus I2 plus I3 equal to 0, but that actually gives me 10 plus I2 plus I2 plus 30 plus 2I2 over 3 equal to 0. And then since I hate fractions, my next move is going to be multiply by 3. Or you could work with fractions. I mean, it's up to you, right? Goodness gracious, we're already 20 minutes into this. These take forever. I mean, it just takes a long time to solve 3 equations and 3 unknowns. And it's not particularly easy to set up the equations here when you're first starting either. You do get faster at this, you know, hopefully. So we get 30. This is 2 times 3 is 6I2 plus 30 plus 2I2 equals to 0, also known as 8I2 equal to minus 60, I guess. So I2 is minus 60 over 8. So this tells me that if I put the units back in, I2 is what? .5 milliamps. Negative 7.5. Yeah, minus 7.5 milliamps. Milli because we divided by 1,000, so that gives us like 0.001, you know? So there's that, and then we can figure out what I1 is, right? So I1 is 10 milliamps plus 2 times minus 7.5 milliamps, which is, I think that's a minus 5 milliamps. And then that makes I3 equal to minus I2 minus I1, which I believe is going to give us, you know, 7.5 milliamps plus 5 milliamps, 12.5 milliamps.
So on the original,
I like this example. This example, by the way, is like right where I'd like the difficulty of like a moderate to difficult test question on this to be. Right about here.
so does that mean that for the currents, the I2 would be backwards, the I1 would be backwards, but the I3 would stay as is?
Mm-hmm.
Cool.
That is what that means. So let's see here. What's the voltage at A then? See, we should be able to write the voltage at A as being V1 minus V1 minus I1 R1. But that is actually a plus, isn't it? So we get 20 volts minus a minus 7.5 milliamps times 1 kilo ohm, which gives me 27.5 volts.
And then if you do it the other way, it should equal the same thing.
Yeah, let's check it. So we should also get the VA if we go like over rats. Well, yeah, I mean, you're trying to find the voltage relative to ground, so I guess you have to, in some sense, do that, yeah. But you see, we could reach A by a different path from ground. Like I was, in my previous equation, I was literally thinking about going bop, bop, like that, right? But I could also think about like this. beep, bop, right? So V3 minus I3R3 should also give it to me. Which would be 40 volts minus 12.5 milliamps times 3 kiloohms. Uh-oh, that feels wrong. Oh, man. Oh. Oh. Rats. Oh, wait a minute. What's I1?
I1 is -5.
Yeah. Let's try, what's 20 minus 5 is 15.
But it's positive, so it'd be 25 still.
Oh, 25?
Yeah.
All right. But that's not,
Correct.
yeah. What? Oh, man. All right, so what's 40? Oh, man. This does not, dang it, that's 2.5. Obviously, we have something is wrong. Oh. What do we get from the middle branch if we think through that? I get
Oh, actually, never mind.
10 volts minus, I think it's the same pattern, so I think I should still have 10 volts minus 10, yeah, so VA is 10 volts minus I2R2, right? Which is 10 volts minus, well, yeah, that's minus 7.5 milliamps times 2 kiloohms. That would, well, that's 25 volts, isn't it?
Yep.
Huh. Well, I guess if I mean, which makes me wonder, what am I just not seeing about the other one? I'm missing something dumb. Well, I really need to bring my glasses. I can't even read these things. Let's see here. Oy.
Never mind.
3 minus I3 R3. I3 was 12.5. Well, I mean, it's possible that I've solved the equations wrong. Let's let's double check my solution with technology. So what I'm doing is I am going to one of my favorite websites, and we are going to look at what is the reduced row echelon form of a 3x4 matrix. I'll show you the calculation here. So I'm working out what's the reduced row echelon form of the matrix 1, 1, 1, 0. That's my first equation. My second equation is 1 minus 2, 0, 10. My third equation is all it takes is one of these numbers being wrong and everything falls apart. It's so picky. It's very unforgiving. It just takes one arithmetic mistake in all of this and it all falls down. Obviously something's wrong. I don't think my interpretation of voltage is what's off. Pretty sure about that. If that's off, then we're in big trouble. Then you should just find somebody else to teach the course, probably. Maybe I shouldn't say that. Let's see here, 10. 0 minus 2, 3, 30. After 7 row operations, it tells me, uh-oh, looks like I made a mistake in the algebra. Well, that's good news. That's really good news. Because I would much prefer an algebra mistake to an interpretation mistake. Algebra mistakes will always be with us. Interpretation mistakes are much more insidious. Minus 60. Minus 60 over 11, and 70 over 11. So we should have gotten I2 is negative 60 over 11. Let's see where we went wrong.
Your I3 for the third equation, if you plug in your I2, you get I3 equals 5. 30 minus 15.
Well, yeah, but what I'm saying is that there's an error up here. So like whatever. This is. I mean, unless I've misinterpreted the equations, this tells me that I1 is minus 10/11ths, that I2 is minus 60 over 11 milliamps, and that I3 is 70 over 11 milliamps. What this does is it does row reduction, which is a technique we learn in Math 221 or high school or whatever, to uniquely solve a system of equations. And so what it's doing is it's like adding equations or scalar multiplying them to each other and changing the form of the equation, so it eventually just becomes, this means I1 is minus 10/11ths, I2 is minus 60/11ths, I3 is that, like if you uninterpret the box of numbers back into an equation. So if I trust the website, have I put these numbers in correctly? Is this right? 1, 1, 1, 1 minus 2, 0, no I3 here, and then a 10, right? Minus 2, a 3, but there's no I1 here, so a 0 here, right? Okay, great. Which means, in retrospect, there has to be an error here.
The I2, for the I1, it's equal to 10 plus 2I2, but then up there it's 10 plus I2 only.
Oh, is it just that? Look at that. You know what he's talking about? Is this what you're telling me? Maybe you're telling me this, I don't know. I have a hard time hearing you guys sometimes because I'm suspicious of my ability to be gullible. So that was supposed to be 2I2 because it's this is that. I think that was it. So that means this gives you us a 3 times 3 times 3 is not, it's 9. That makes this a 9. 9 plus 2, 11. And voila. Is it worth your time to figure out how to do this on a calculator? Yes, it certainly is. Right? I can do this kind of math on this calculator. It's got row reduction in there. You just have to I go shift matrix. It gets me to this here. Yeah, that's a toy. That's no good.
This one doesn't work.
Yeah, that's no good. Sorry. But, I do matrix A. I hit enter, and it brings me to this here 3 by 3 matrix. But I could make it, I could change the size of it, I could make it 3 by 4, and I can do this in the calculator. Now, you don't need it, because technically, yes, you can do the math by hand. I'm not trying to make a mistake on purpose. It's just, we're fallen beings, right? We're not perfect. So we will do these things. Do I know how to solve equations? Yes, I do. Do I still make mistakes? Yeah, but you have to be, this is why I'm checking my work with you guys, is I don't want to sell you a bill of goods. That's why we're doing this. It's because I have fear. I have learned to mistrust my results for a 3 by 3 system, to double check, Anyway, now that we've got this, let's fix it. So I2 is what, actually, in terms of approximate? Oh no, the cough is upon me. 60 divided by 11. So that's about minus 5 point, we'll keep 3 digits, 5455 milliamps. And then I'm supposed to do 10 milliamps plus twice that, right? So multiply that times 2. And then, yeah, it's pretty slight, isn't it? It's minus 0.909, something like that, milliamps. And then I do, 5.455 plus 0.909, and that gives me my I3, which was oh man, okay, yeah, well, fine, 6.364 milliamps. Let me double check with my other answer. What's 70 over 11? 6.364, yeah. Okay, that's apparently the real. And so we do 20 volts minus not 5 milliamps, but 0.0909 milliamps, right? Which gives us actually 20.909 volts. And we can compare that to 40 volts minus not 12.5 milliamps, but 6.364 milliamps times 3. So I get 20.909 volts, right? Yay. And again, down here, we can take 10 volts minus, I2 was minus 5.4, oh no, 55 milliamps. Yowzers. So we got 10, well, 5.5 times 2, is 10.9 plus 10. So again, about 20 point. I've got some round off error over here because I messed up, but it's 20.91 is what I got. But you know that's just a mistake on my calculator's part. Are we good? Oh, it feels so overwhelming when you go through all that work and it's inconsistent, right? I mean, like, it's so maddening.
That's the type of question you would ask for, like, understanding the basic type of curves.
Yeah, this would be a moderate to difficult test question on, do you understand circuit, how to, like, solve a circuit. If I put this on a test, it means that if I put this kind of thing on a test, that means that I'm expecting that it takes you 15 to 20 minutes to solve this problem alone. Yeah. So you guys have not had Math 221?
Is that applied linear algebra?
Mm-hmm. There are some trick formulas you can learn to solve systems if you don't want to get a calculator. There's something called Cramer's rule that'll allow you to just write down solutions. And kind of like the deal with these, if you think about 3 equations and 3 unknowns, if you can solve one of the variables, then you got the rest of them, right? So if you know a shortcut to solve one of the variables, that could be helpful. Since you guys are here, I'll share it with you. This is not physics, obviously. It's just linear algebra, but if you've got 3 equations and 3 unknowns, and you're trying to solve them. So it's something like, so we use the notation like A times, I'll use x, y, z for the equation. So times this is equal to, like b1, b2, b3. So let me just give an example. So like, suppose you got x plus 2y plus 3z is equal to 7, and 4x plus 5y plus 6z is equal to 0, and 7x plus 8y plus 9z is equal to, oh, let me not do that. Let me make this just a z. Otherwise, I think I might be in trouble. 0. Suppose you want to solve this 3 equations, 3 unknowns. So what you do is you write down the so-called coefficient matrix for the problem, which is 1, 2, 3, 4, 5, 6, 7, 8, 1. And you calculate its determinant. So the determinant, let me not write that. Determinant of A is 1 times 5 minus 48 minus 2 times 4 minus 42 plus 3 times 32. Yeah, 32 minus 35. So let's take a second, work that out. What do you got? Negative 43. Plus 76, all right. And then minus 9. That feels right. So what's that? 24. All right, cool. That feels right. 24 plus 52 is 76, yeah. Okay. So Cramer's rule, which you can solve for any variable you want. The other nice thing about Cramer's rule is you could use it to solve for whichever variable you want. You pick it. Do you want me to solve for x, y, or z? Y. All right, to solve for y, Cramer's rule says you take the determinant of A, 1, 4, 7, and you put this right here in place of the y. And then the other is still the same. And you divide by the determinant of A, which we already know. All right? Now, let me do something a little bit sneaky here. If we plus minus, this is minus 7 times 4 minus 42 is actually what that determinant is. Which is, you know, whatever that is, but 7 times 38. 7 times 38 over 24.
Like 11.08.
Okay, so like 11.08. Okay, great. Approximately. That's kind of nice.
And that would be.
But the downside of it, of course, is you're resting on your ability to calculate determinants carefully, which is dangerous because determinants are a pain. Now, on the other hand, if you use the calculator row reduction method, it's a far safer thing. If you're just letting the calculator do all the work, right? Like, let me put this same problem into my calculator, matrix calculator online, which you can, again, you can do, and even the Casio 115EX, it's in there. If you get one, I can show you how, if I'm awake. So 1, 2, 3, what was the 7? And then 4, 5, 6, 0, 7, 8, 1, 0. I submit. So, oh man, no. So we made a mistake somewhere. Golly, 1, 2, 3, 7, 4, 5, 6. Assuming I didn't punch a number in wrong, which is, I'll check on it in a second here. And so I don't know. I mean, like, you can. I don't expect you to learn these methods. I'm just saying that they can reduce your cognitive load on the next test if you have a way to double check your systems of 3 equations and 3 unknowns. It's nice. Not that you have to. So the original matrix was 1, 2, 3, 7, 4, 5, 6, 0, 7, 8, 1, 0. Yeah. And it turns out minus 301 divided by 24. 24 is good. 100. Oh, wait a minute. No. Look, I was too. Check this out. Yeah. Eh? Yeah. All is not lost. This is 266 over 24. So, yay. But of course, I do think the matrix method is way better than Cramer's rule because it doesn't get you just one answer, it gets you all 3 answers. And, you know, if you're going to use a calculator anyway, you can also calculate the determinant with your calculator. That's also in there. That becomes a much more important thing to know about for like a 4x4 matrix.
What type of calculator do you use?
I'm just talking about the Casio 115ES Plus. I've had this for years. It's in like 20 bucks in Walmart. It's nothing special. It just happens to have under it a matrix. See, it happens to have this matrix thing right here. So, you know, I can get in there and do stuff like 2, 1. There's a way to change the size of the matrix. I've forgotten how to. I mean, I had to fuss around with it. I don't use it that much, you know.
Mm-hmm.
But
I
anyway.
used to have something like that when I was super young, but then I lost it.
About this, yours will do it.
I found the button, but I don't know how it works.
So you just go like, there's a TI-84, so I think go matrix maybe. Matrix list, no, that's not what we want. Clear, let's see here. Ba-dum.
Let me get that something.
Mode maybe, normal.
There's a matrix right there. I hit second.
Matrix, oh
Hit
yes.
second.
Second, matrix, names, oh
Then I
yeah.
went over to math.
Well, just,
And
oh,
I
but
think that was it.
just stay with one. Names A. Okay, well, nah. Yeah, so we go matrix, and maybe edit one. And you want, let's say, 3 by 4. And then 1, 2, 3, 7.
Would you say a calculator like
4,
this is about as advanced as we need for any of our classes?
I think so, but I mean, you might be able to get away with more in an engineering class. I try to forbid these graphing calculators. I don't typically allow
I was like,
in the math courses.
I've wanted to get a graphing calculator, but I just don't have the money. So I'm not going to get
Well,
it.
I don't, honestly, like, so let's do math. Now, see down here? Maybe it's down further. Ref. And then A, how do you get A in there?
I think it's alpha.
I went back to your matrix list and then I got it. Oh man, come on. All right, well, let me ref that. This is gonna be hilarious. Well, it seemed like what I just did should work, Maybe if I do answer. Check it out, you. Oh, what? Oh, see, this is why I didn't want to put this is why I didn't put the 9 in the last column. If I put the 9 in the last column, you get this equation, which means that x minus z equal to 0, y plus 2z equal to 0. And the last equation is 0x plus 0y plus 0z equal to 1. That means it's inconsistent. I should have put, I was supposed to put a 1 there. And so that's why it didn't turn out the same. But you can do everything there. You just need to practice a little bit, If you Google like how to use my TI-84 to solve equations, somebody will have made a nice YouTube video that, But I don't know. I mean, I'm right on the, if I had one of those, I'm right on the edge of, do I want to figure it myself by just punching buttons, or do I want to watch a video of, some dude, I don't know. I usually try to punch the buttons, and if I get frustrated for like 5 minutes, I'm like, all right, fine, I'll watch a video. Say everything else, Oh yeah, go for it. All right, let us try to work some problems. Let's try to work more than one problem in this problem session, right? Maybe.
An hour.
Yeah, we're 53 minutes in. You know what? I'm going to stop the tape right here.